NVIDIA just dropped something that completely changes how AI learns to play games. And honestly, the gaming and robotics communities are still processing what this means. We are talking about Nitrogen, a 500 million parameter model that can play over 1000 different games straight out of the box, learns entirely from watching YouTube videos, and achieves up to 52% better results than models trained from scratch. And the crazy part is that NVIDIA built this whole thing by borrowing an idea from Twitch streamers. Let me explain why this matters and why every game developer and robotics researcher should be paying attention right now. Alright, so Nitrogen is basically the first real gaming AI that actually works like a general player instead of a narrow specialist. Most game AI today gets trained on one specific game, cost millions to develop, and completely falls apart the moment you throw it into something new. NVIDIA went the opposite direction. They built one single model that handles action RPGs like Cyberpunk 2077, 2D platformers, combat-heavy games, racing titles, roguelikes with random levels, and even procedurally generated worlds where nothing repeats twice. The model watches raw game pixels at 256 by 256 resolution, processes them through a vision system, and spits out real gamepad commands. Left stick, right stick, 16 buttons, the full controller layout. No scripts, no cheats, no reading hidden game state. Just pure visual input to physical output. Here's the thing. Training this kind of model normally takes years of expensive gameplay data collected by hand. NVIDIA found a shortcut that nobody else thought to use at this scale. They went after Twitch and YouTube videos where streamers show their controller inputs on screen. You know those little gamepad overlays in the corner that show exactly which button someone is pressing? NVIDIA collected 71,000 hours of those videos, ran them through a smart filtering system, and ended up with 40,000 hours of clean, labeled data across more than 1,000 games. That filtered dataset contains 38,739 videos from 818 different creators. And honestly, when you think about it, this is the smartest data collection move anyone has made in embodied AI. Instead of paying humans to play games and manually label actions, they just scrapped public gameplay and let a computer vision system extract the controller inputs automatically. Now, the extraction pipeline itself is actually pretty impressive. NVIDIA built a system that first locates the controller overlay using something called template matching. It checks 25 random frames per video, runs key point detection with Shift and X fit features against a library of known controller templates, figures out where the overlay sits, crops it out, and then trains a segmentation model to read joystick positions and button presses from that cropped region. And to make sure the AI doesn't cheat, they mask out the overlay area from the main gameplay frames. So the model never sees the controller during training. It only sees the game screen and the action levels. The accuracy here is wild. They hit 0.84 R-squared correlation for joystick positions and 0.96 frame accuracy for button presses. That's better than most human annotators could do on messy, low-quality stream footage. The real breakthrough though is how the model generalizes. NVIDIA didn't just train this thing to memorize gameplay. They designed it to understand control at a deeper level. The architecture follows the ZR00T-N1 pattern, which is NVIDIA's robotics foundation model. Yeah, you have that right. This gaming AI is literally adapted from robotics technology. ZR00T-N1 was originally designed to control humanoid robots, and NVIDIA realized the same system that makes robotics move smoothly in the real world also makes game characters move naturally inside virtual environments. For Nitrogen, they stripped out the language and state encoders from ZR00T and kept just the vision encoder plus a single action head. The model uses a Siglet 2 vision transformer to encode each frame into 256 image tokens, then feeds those tokens into a diffusion transformer that generates 16-step action chunks using flow matching. Flow matching is a technique borrowed from generative models like image diffuser. Instead of predicting one action at a time, Nitrogen predicts entire sequences of future actions all at once, which keeps movement smooth and coherent across time. And the numbers actually back this up. NVIDIA tested Nitrogen on 30 tasks across 10 commercial games. 5 of those games were 2D, 3 side-scrolling platformers and 2 top-down roguelikes. The other 5 were full 3D games, 2 open-world titles, 2 action RPGs, and 1 combat-focused game. They split the tasks into 3 categories: 11 combat tasks, 10 navigation tasks, and 9 game-specific challenges. And without any fine-tuning at all, just the base model trained on the full 40,000 hour datasets. Nitrogen heat completion rates between 40% and 60% across the board. That includes both memorization-friendly scenarios where the models saw similar gameplay during training, and zero-shot generalization in procedurally generated worlds where every level is brand new. To be clear, those numbers are insane for a model running completely blind on games it was never specifically trained for. The standard approach to game AI right now is reinforcement learning, where you let the model play millions of times, reward it for good behavior, and punish it for mistakes. That method produced superhuman performance in games like Dota 2 and StarCraft 2. But those agents are narrow, expensive, and locked to one game. They cannot transfer anywhere else. Nitrogen skips reinforcement learning completely. It just watches humans play and copies what they do. This is called behavior cloning, and it's way cheaper, way faster, and way more flexible. The trade-off is that behavior cloning models usually hit a performance ceiling because they can only be as good as the humans they learn from. But when you train on 40,000 hours of diverse gameplay from hundreds of creators with different skill levels and play styles, that ceiling gets pushed way higher. Now, here is where it gets interesting. NVIDIA ran a second set of experiments to test transfer learning. They held out one game from the training set, pre-trained Nitrogen on everything else, and then fine-tuned it on the held out game with limited data. They compared that against a model trained from scratch on the same game with the same data and compute budget. The results were massive. On an isometric roguelike, fine-tuning from Nitrogen gave about 10% relative improvement. On a 3D action RPG, the average gain jumped to 25%. And for some low-data combat tasks, where they only had 30 hours of training footage, the improvement hit 52%. That's more than double the performance in some cases. And honestly, that kind of transfer is exactly what everyone has been chasing in embodied AI for years. The ability to pre-train once on a huge dataset and then rapidly adapt to new environments with minimal additional data. NVIDIA just proved it works for gaming agents. The crazy part is that Nitrogen doesn't just learn motor control. It learns strategy, timing, and context-specific decision-making. In one test, they dropped it into The Witcher 3, a massive open-world RPG with complex combat mechanics, inventory management, and dialogue trees. Nitrogen handled combat encounters, navigated through cities, and even executed multi-step objectives like tracking down quest markers. In Cyberpunk 2077, it drove vehicles, shoot weapons, and explored Night City without getting stuck on geometry. In Rocket League, it controlled car movement, aerial maneuvers, and ball physics. These are all widely different control schemes, camera angles, and pacing demands. And the same 500 million parameter model handles all of them without any game-specific modifications. And to put this in perspective, OpenAI's VPT model, which played Minecraft by learning from internet videos, was trained on about 70,000 hours of data but only worked on one game. Google's Sima, which is a multi-game agent, was trained to follow text instructions but needed human-level demonstrations and still struggled with long horizon tasks. NVIDIA's Nitrogen covers more games, uses automatically extracted levels instead of expensive human annotators, and shows stronger transfer performance in head-to-head tests. It's basically the first open-source gaming AI that competes with top-priority research projects from the biggest labs in the world. The other major advantage here is the universal simulator system. NVIDIA built a wrapper that turns any Windows game into a Gymnasium-compatible environment. Gymnasium is a standard API used for reinforcement learning research. It defines how agents interact with environments in a consistent way. Observations, actions, rewards, don't flags, all standardized. The Nitrogen simulator integrates the game's system clock to control simulation time and supports frame-by-frame interaction without modifying the game's code. So you can literally plug any commercial game into the system as long as it uses the system clock for physics and timing. That means Nitrogen becomes a testing ground for embodied AI research without needing access to custom simulators or game engines. Researchers can benchmark their agents on real AAA titles, compare results, and iterate fast. In fairness, Nitrogen still has limits. It only works well on games designed for gamepad control. Action games, platformers, racing games, fighting games, those all work great. But games that rely heavily on mouse and keyboard, like real-time strategy titles or MOBAs, don't transfer as cleanly because the action space is completely different. The model also struggles with extremely precise timing challenges, frame-perfect inputs, pixel-perfect jump, speedrunning tricks. Those are still beyond what behavior cloning can handle, and it doesn't understand game mechanics that require reading text, managing complex inventories, or interrupting abstract UI elements. The model sees pixels, not game state. So if a game requires reading quest logs or pausing crafting menu, nitrogen gets lost. But the bigger picture here is that NVIDIA is positioning nitrogen as the first step toward general embodied intelligence. Jim Fan, NVIDIA's director of AI and distinguished scientist, said, "This is just the beginning. The long-term goal is to use gaming as a training ground for real-world robotics. Games are perfect for this because they offer visually rich, interactive environments with infinite diversity, zero hardware cost, and instant reset. If you can train a model to navigate Elden Ring, dodge attacks in Dark Souls, or solve puzzles in Portal, you are teaching it skills that translate to real-world navigation, obstacle avoidance, and task planning. The control loop is the same. Observe the environment, predict an action, execute the action, observe the outcome. Repeat. Whether that loop happens inside a game or inside a warehouse doesn't matter to the model. And that connection to robotics is already proven. The ZR00T N1 architecture that inspired Nitrogen was originally designed for humanoid robots. It's a vision language action model that takes in camera feeds and text instructions, processes them through a dual system setup inspired by human cognition, and outputs precise motor commands. System 1 handles fast reflexive actions. System 2 handles slow deliberate planning. Nitrogen adapted this architecture by stripping out the language component and focusing purely on vision to action mapping. But the core transformer architecture stays the same. That means any improvement to Nitrogen directly benefits robotics research, and any improvement to ZR00T directly benefits gaming AI. It's a two-way feedback loop. NVIDIA also open sourced everything. The full dataset, the model weights, the evaluation suite, the simulator code, all of it is on Hugging Face and GitHub Vernon. Anyone can download the 500 million parameter checkpoint, plug it into their own games and start experimenting. The dataset alone is a game changer. 40,000 hours of labeled gameplay covering more than 1,000 games is the largest open source gaming dataset ever released. Before this, most researchers were stuck training on a handful of titles with maybe a few hundred hours of data. But they have access to a dataset that spans 846 games with over 1 hour of footage each, 91 games with over 1,000 hours, and 15 games with over 1,000 hours each. The game distribution is insane too. Action RPGs make up to 34.9% of the total hours. Platformers are 18.4%. Action adventure games are 9.2%. And the rest is spread across fighting games, racing games, roguelikes, puzzle games, and more. The community response has been pretty wide. Researchers from NVIDIA, Stanford, Caltech, University of Chicago, and UT Austin, along with the MindDojo team, all collaborated on this project. And they are testing it like the GPT movement for embodied AI. Some people are calling it the foundation model for actions. Others are saying it's the first real step toward artificial general robotics, and honestly, both angles make sense. Nitrogen proves that you can scale up imitation learning the same way OpenAI scaled up language models, collect massive amounts of diverse data, train one big unified model, and watch emergent capabilities show up. The model wasn't explicitly taught how to handle combat or navigation or exploration. It learned those skills of exposure to thousands of different gameplay scenarios. That's exactly how large language models work. They weren't taught grammar or reasoning. They absorbed those patterns from text. Of course, there are still skeptics. Some people argue that gaming is too easy compared to real-world robotics because games have predictable physics, clean visual inputs, and no sensor noise. Others point out that Nitrogen's 52% improvement only shows up in specific low-data combat scenarios with just 30 hours of training footage and drops closer to 10% on average across other tasks. And there is definitely truth to both points. Games are simpler than reality, and the transfer gains aren't consistent across all scenarios. But the counter-argument is that this is Vision 1, the first open-source multi-game foundation model trained entirely from internet data. The fact that it works at all is already a huge milestone, and the fact that it outperforms training from scratch in every single tested scenario means the pre-training is doing something real. The model is learning general control principles that carry over to new environments. One thing I'm really curious about now is how this compares to OpenAI's approach with embodied agents and how Google's DeepMind team responds with SEMA 2. Both of those projects are closed source right now, so we don't have direct benchmarks, but if Nitrogen's results hold up under adversarial testing, NVIDIA might have quietly leapfrogged both of them. The combination of open source release, massive dataset scale, robotics architecture crossover, and proven transfer performance is a really strong package. And the fact that it all runs on standard gaming hardware instead of requiring specialized simulators or expensive compute clusters makes it way more accessible to researchers outside the big labs. That's where we will wrap it up. Drop your thoughts below on whether you think gaming AI will actually translate to real world robotics or if this just hype. Make sure you're subscribed, hit that like button, and I will see you in the next one.